Hello and welcome to Introduction to Calculus. In this video, we're going to see the last application of a tangent line in calculus. Please make sure you print tangent line and local linearity number 3 before you watch the video and follow along. This video will closely be related to what's on my note. Let's begin. Recall that in the first unit, we had defined the average rate of change of a function f between two inputs as f of b minus f of a, that's called the total difference between a and b, right, divided by b minus a. When we looked at the instantaneous rate of change, rate of change, we fell upon the definition of the derivative, the instantaneous rate of change at a value, right? Okay, now in that first unit, you will also recall that we had defined another ratio, the relative change of a function between two inputs, let's say a and b. Do you remember it? You take the total difference, f of b minus f of a, but this time you divide it by the initial output, f of a. Okay, now what becomes of this ratio if you're looking for an instantaneous translation of it? What's going to happen there? What are we going to fall upon? Well, actually, it is not exactly this ratio that will have an instantaneous translation. It's going to be the relative rate of change of a function between a and b. And you remember, to find that, you divide the relative change by the difference in input, b minus a. So it gives you a relative change per unit of input. Now, this ratio will be translated instantaneously. That's what I'm going to show you in this video. Let's begin by recalling the relative change and the relative rate of change. So suppose I consider the function x squared, f of x equals x squared, and I'm taking two input, a equals 2, and I'm going to take b equals 5. What is the relative change of the function between 2 and 5? Of f between 2 and 5. So it's very simple. It's f of 5 minus f of 2 divided by f at 2, right? So f of 5, 5 squared, 25, minus 2 squared, 4, divided by 4. So this is 25 over 4 minus 4 over 4, right? I'm breaking the sum. And this is what? 25 over 4, that's 24 over 4 and 1/4. So it is 6.25 minus 4 over 4 minus 1. And so it is 5.25, or if you want to state that as a percent, 525%. So what does it mean? It means that f of x increased by 525% when x increased from 2 to 5, right? From 2 to 5. That's what it means. Okay, so now let's look for the average, the average relative change, which is called the relative rate of change. What is the relative rate of change of the function of change? So of the same function between the same input, okay? So what you're going to do here, you're going to take f of 5 minus f of 2 over f of 2, that's a relative change, and you're going to divide it by the difference in input for every unit of input, okay? So you're going to find 5.25, right, divided by 3. 5.25 divided by 3 is 1.75, or again, 175%. What does it mean? It means that f of x increased by 175% per unit when x increased from 2 to 5. For for every unit between 2 and 5, f of x increased by 175%, right? So when x goes from 2 to 3, you add 175% to the output. From 3 to 4, you have 175% of the output, and from 4 to 5, another 175%, okay? Okay, so let's now go over a second example. For this one, I need my notes. Alright, so an efficiency study of the morning shift at a certain factory indicate that an average worker who is on the job at 8 a.m. will have assembled f of x unit hours x units hours later. So f of x unit x hours later. Find the relative change between 10 a.m. and 1 p.m. Okay, so that seems to be pretty straightforward. 10 a.m. be careful of the scale here, okay? So 10 a.m. corresponds to x equals 2, right? It is hours later after 8 a.m., so that's x equals 2, while 1 p.m. that corresponds to x equals, so from 8 to 1 you have 5, okay? So to find this relative change between, so relative change between 10 a.m. and 1 p.m., what is that going to be? So that's going to be f of 5 minus f of 2 divided by f of 2. Okay, hey, we're going to use a calculator for that. Okay, so I'm going to enter this function, which is negative x cubed plus 6x squared plus 15. So negative 1, 6, 15, and 0. So let's take the calculator. All right, let me go to my y equals. So in y1, I'm going to have negative 1, negative x cubed, 6 and 15, I think, plus 6 plus 15x. Let me check that. Negative 1, 6, and 15. Negative 1, 6, and 15. Yeah, that's it. Okay. And now I'm going to go on my home screen. And, okay, from the home screen right here, so we have a difference at the numerator of the fractions, so I need to open some parentheses. So y1 at at 5 we said, minus y1 at 2. Let's close the numerator, divided by y1 at 2, initial output. So it is 1.17, so it's about, let's say about 1.17, so it's about 117%. Okay, so that means the number of unit produced at 1 o'clock has increased by 117% in comparison to the number of units produced at 10 o'clock. Okay, there was an increase of 117% in the number of units produced between 10 o'clock and 1 o'clock. Okay, now let's find the relative rate of change. So for the relative rate of change, let's call that RRC. So it's going to be the relative change divided by the time, so that's 3 hours, right? So it is about 1.17 divided by 3. So let's do that divided by 3 right here, and this is about 0.39, so about 39%. So about 39%. So every hour between 10 a.m. and 1 p.m. the number of items produced increased by 39%. Okay, all right. Let's continue with the lesson. Okay, so let's look at the formula of the relative rate of change of f between x and a. It's f of x minus f of a divided by f of a divided by x minus a. Okay, if x is very close to a, so for x very close to a, we have a very good approximation for f of x, which is the tangent line approximation. That's why this lesson is an application of the tangent line, okay? So what do we have for the output f of x using the tangent line approximation? We have the output at a plus the rise from this output, right? So it's the slope, f prime of a, times the run, x minus a, right? If we use this very good approximation, because we're very close, x is very close to a, if we use this approximation in this ratio, what do we find? Well, let's check it out. I'm going to replace f of x by this expression right here. So what do we have? F of x minus f of a. So it is f of a plus f prime of a times x minus a right here. Okay, that's my f of x. Now let's continue. Minus f of a over f of a divided by x minus a. So what's going on here? Well, the f of a will cancel, and you're left with f prime of a times x minus a divided by f of a divided by x minus a. So how do you divide two fractions? This is the main fraction bar right here, right? You multiply by the reciprocal. So it's f prime of a times x minus a over f of a. This is x minus a over 1, so times 1 over x minus a. That will simplify. And what do you find? You find f prime at a divided by f at a. So you don't even have x in there. There's no x in this formula. This is actually what we call the relative rate of change at x equals a. So this is the instantaneous relative rate of change of a function at an input, right, at x equals a. All right, let's apply it in a few examples. You will see it's very simple. Okay, so we're supposed to estimate the relative rate of change of a function at the indicated value. To find that, to find the derivative at the value, you will use symmetric difference, blah, blah, blah. We know what it means. Okay, so my function is f of x equals square root of x plus 3. And these are the value at which I want to find the relative rate of change. I'm going to present things in a table. It's going to be much easier. So on the first row, I have x, and I will have x equals negative 2.9, negative 2, negative 1, and 0. And on the second row, I will have f prime of x divided by f of x. Here we go. So let's use a calculator, shall we? So the function is square root of x plus 3. So here we go. In y1, I'm going to enter right here, delete. I need the square root of x plus 3. In y2, I have my symmetric difference. That's okay. And in y3, actually, you know what? Let me not look at the output at y1. I don't want to see it. So I'm going to push enter. Output at y2, I don't care about it. And now in y3, I'm going to enter my relative rate of change, f prime over f. So that's y2 divided by y1, here we go, f prime over f. Okay, and now let's check out the table of value. I think I'm still on ask in my table. Yeah, so the values are negative 2.9, negative 29, sorry, negative 2.9, negative 2, negative 1, and 0. And these are the percent. So 500%, 50%, 25%, and about 17%, right? So let's write that. So this is 500%, 50%, 25%, and about 17%. How come this ratio decreases so drastically? Well, again, this is something that's going to be due to the shape of the curve, just like what we talked about yesterday in the lesson, right? 1, -2, -3. If you look at square root of x plus 3, it changes like this, okay? So if you look at the instantaneous relative change at relative rate of change at -2.9 right here, you see between two output right here, the function is going to increase a lot very quickly. Actually, it's very close to the nose right here, and the nose is almost, it's never vertical, right? But it's very, very steep right there. Very steep, right? So very quickly, the function will increase a lot. But then, if you're at -2, right, it doesn't increase as much around -2. At -1, it's even less, and at 0, even less, right? So it's normal the further away you go on the right, and the less the ratio, because between two values, or actually not between two values, at a value, the instantaneous relative rate of change goes diminishing, okay? I hope this is clear. I'm going to let you work out the second example right here, this one, number 3, and I will do the last one. So the last one, we're going back to the example we did above, but this time we will want the relative rate of change at 10 a.m. and at 1 p.m. okay? So this is a productivity function. Let me plug it again in my calculator. -1, 6, and 15. So right here, so it's -1, so negative x cube, 6, and 15. Here we go. I don't need the value, I don't need the output of this function right here, so let me not graph it right here. Here we go. And in y3, I do have my relative rate of change, the instantaneous relative rate of change. So let's check out the table of value. Here we go. And I want it at 10 a.m., so that's 2 hours after 8, so that's at 2. And at 1 p.m., so that's 5. Okay? Well, that's kind of interesting, right? At 10 a.m., the instantaneous relative rate of change is about 59%, right? Let me write it. At 10 a.m., it's about 59% per hour, right? I mean, it's at 10 a.m., but that means it's changed by 59% for every hour, right? But if you look at 1 p.m., at 1 p.m., the instantaneous relative rate of change is about 0%. So they've reached a plateau, and they're not producing neither more nor less. It's just the same amount. It doesn't increase, right? So productivity increase in the morning, which I guess it's normal, right? When you start your shift, you're not going to produce as many items as when you are a couple of hours into your shift, right? But then after a while, then you're not going to just increase that number of items. It's just going to be fairly constant. And this is what this, I believe, is showing us. Thank you for watching.